Hello people, and welcome back to this channel where I am designing and coding a virtual machine for parallel computation of something called activation function. So the context is Tract. Tract is a neural network library that allows you to, once you've done training a network, you can use Tract to run the network on a device, on a phone, on a smart object, and that's the library. And computing a neural network requires, it's essentially computing. So a lot of it is matrix multiplication, which have been already well optimized in Tract. It's not perfect, but it's pretty good already. And there are a bunch of other things, and one of them is activation functions. So an activation function is basically your very mid-school or high school math function. So it takes an x and it returns a y, and it does some computation, and always some computation on the value. So it's very easy to represent it by or to execute it in a for each, where you iterate over all of the values in your input, and what you get is the output that you put in the place of the input, if you want, or in a different place, it doesn't matter. So it's just a for each over an expression on x, and that's very easy. But the fact that it's so simple to represent means that you can get a lot of performance by just using your CPU write, and this means using a SIMD unit and do some parallelization of the computation. And so we started working on that quite a long time ago on this channel. It took us about 10 sessions to get here. And where we are is we have some implementation. So we picked this first block of operation, and I added a few ones on top of it, like Sigmoid, essentially, because it's interesting for different reasons. I mean, it's a very interesting one. It's a very important one in neural network. It's all over the place. And what we did is we define a series of simple operations. So these are the add, mul, etc., which you can see here. This is a move, so this moves A to B, and we define so we have like about a dozen of these operations, maybe a bit more, and we express all of these activation functions in this as a sequence of this macro expression, and then we implement an interpreter for this macro language in assembly directly that will compute over several values at the same time. And so we were there. And so this is a part of our implementation. It's for ARM8. So ARM8 is whatever you get in all the modern phones on the new Apple M1, M2 systems. Basically, everything not Intel is ARM, and all the high-end stuff is ARM8. And so, I mean, when I say Intel incompatible, so I know that beside Intel there is AMD. But so what we did is this is the implementation, and I was interested in revisiting actually the Sigmoid implementation, because it was underperforming. Underperforming compared to what? Compared to, I should have done that before again, and I didn't. So let's try it, and hopefully it will work out of the box. The Sigmoid has been here for a long time. I mean, it's a very important function in neural network, and so I already have handcrafted assembly implementation of Sigmoid, which I can show you. Actually, that's the one. And what we noticed last week is that this, and it's not a big surprise, but this implementation outperforms the new one, the one based on the VM, by quite a significant factor. I don't remember exactly how much, but it was important. And so I started to wonder where was the overhead. And there is an overhead, an obvious one. It is that this function, it doesn't have any overhead at all. That's the handcrafted one, because it just computes the sigmoid. It's actually a compiled sigmoid implementation. Whereas the other one, the one that we did over the past few weeks, it's an interpreter. So besides doing the actual work of computing the sigmoid, it has to look at the instruction flow, the macro instruction flow, pick the next instruction, decode it, jump to the right place, actually do the work, and then go back to the next instruction and do this loop all over again. So depending on the ratio of time spent in doing the actual stuff and doing the interpreting stuff, we were right to expect some difference in performance. But that's not all of it. Something else is, if you look at these, so the sigmoid, the computation of sigmoid is essentially you doing some min and max things to keep in a range where the sigmoid is meaningful, because in F32 representation, as soon as you below minus something, minus 12 or 20, I don't remember, or above 12 or 20, the only value that the sigmoid will get is 0 or 1. 0 for the very negative part and 1 for the very positive part. And in between it does just a big S, so the name sigmoid. So first you need to clamp yourself to the area of interest, so the one where you actually have the S, not the flat one. So it doesn't matter that you shift to the end of the range value which are to the right, because after this point sigmoid is essentially constant, or before in the negative. That's the reason why there is this max and min at the beginning. And then you compute two polynomials on x2. So this is where we compute x2, so x squared. This will be the computation for the first poly up to there. Yes, the impl command numerator. And then we compute the denominator, which is a second polynomial. That was a mosquito. Sorry for your ears. And then we compute the second polynomial, which is also, the second polynomial will act as a denominator, and as we have a numerator and a denominator, obviously we do a division. And so computing a polynomial, if you look at the sequence of instruction, you can see this long list of duplication, then FMLA. And let's have a look at this, because if I don't have the Raspberry Pi, I'm not sure if what I'm trying to do tonight makes a lot of sense. Process didn't exit successfully. Yeah, something is wrong, but that's so with the command. So what if I do just this? It looks like the Raspberry Pi is working, so we should be all right. Okay, so we have this sequence of FMLA and or not. No, because it's the AirSync which is failing, which is not a good sign, because so the Raspberry Pi is actually supposed to be under my desk, and it looks like it's there. So the good news is I can reboot it by hand. That's what I'm doing right now. Here we go. In the meantime, so let's talk a bit more about this. So we have duplication and FMLAs, and FMLA is a fuse, multiply, and add. And the reason why there is this pattern is, if we look at maybe the Rust implementation will be easier to understand. So it's in generic. Yes, download please. And so that's what the pattern is about. So at the very beginning, we initiate with, it's not super clear, but yeah, so we're putting, so V24 and 25 and 26 and 27 represent the P variable over there, store the P variables. And we start by putting alpha 13, so it's in this location, V0S3. We start by putting this into P, and then we are multiplying by V20, which is x squared. So that's this. Trying not to so we're multiplying, so there is a trick, sorry. So V0S3 is actually alpha 11 and V0S2 is our starting point, so it's alpha 13, so it's P, so P starts in V0S2, and here we're doing V0S2, so that's P, this one, time V20 for S, so these are the values for X2, and we are storing it in accumulation on V24, and V24 was initialized to alpha 11. So these two lines do over these four values, they do this line and this one, and then it's essentially the same, except there is a bit of an inversion. But so let's look at the following line. We are doing x2 times p, so and we're adding alpha 11, alpha 9. So alpha 9 comes from v1s, so we are putting alpha 9 in v28, and then we are accumulating on v28 the product of v20, which are the x2s, times v24 for s, which was the previous value of p. So we are starting in v24 to v7, so these are the 16 values that we are operating on. And in this stage, we are moving to, P is now in v28 to v31. And then it comes back to, for the next line, the one that does alpha 7, I guess, we are coming back to v24 to v27, then back to v28 to v31, etc., until we get to the final multiplication here. So single multiplication here that we do in place, and in v16 to v19 we should have kept our x value. Yeah, that's where we load x. So with this implementation, half of the lines are actually doing something that matters. Meaning, if we count, if you want to simplify a bit, we can say that FMLA is an addition and a multiplication. So, and it also operates on 4 values, but that's neutral in our computation. So we have this, which is a bit of an overhead, and this that does 2 things, the multiplication and the addition. So basically, we are doing one arithmetic operation over 4 values for each instruction in this stream. Now, if we look at the new implementation, and even without considering the overhead of the interpreter, let's, oops, sorry, oops. Okay, I don't think we need this anymore. ARM 64, ARM 64, SIMD, wrong place. ARM 64, ARM 64, SIMD, activation. Okay, so the right instruction is FMA, I think I called it FMA. And so so the first difference is in the handcrafted implementation, we were operating on 4 values, so that's 16. Here we are operating on over 8 values. So it should be faster actually, because I mean, we are amortizing some overhead here because for the same overhead we do more computation. But the problem is for each FMLA, we have one DUP and also one AND which act as a move. Because the sequence that we have to do is to do this. We start by moving A to D, which act as a free register. We are then copying the constant into A, and finally we are multiplying we're multiplying B by D, so B is still B and the D is now A, and we are adding it to A, which now contains a constant. So that's 3 stage, 3 operation for 2 actually useful operation. So I was wondering if there was not a way to do this better. And I think there is, because if I'm doing instead A gets A times B, then A gets A plus K, then I have 2 single operations, and it should be, I mean, yeah, that's 2 ops instead of 3. So it should be, it could be faster. So that's what I wanted to try. Let's see if my Raspberry is back online. Please be back online. It's not. It's not. What else can I use? Why is it not online? It should be back online. Let me just have a look at my 0-tier configuration. Oops. Not in front of you, because you don't have to know about this. So login, blah blah blah. And let me see if I can see on 0-tier the PC seems to be online. Nope, the PC is not online. It's interesting. And the Raspberry Pi is online. So the problem is on the PC side. So we will try to restart 0-tier. It wasn't planned. System control, restart 0-tier. 0-tier 1, later. Okay. Reloading the 0-tier dashboard. And my PC is there. So now, suspense, but this might actually work. In the meantime, let me go back to my Twitch screen. Yes, I'm there. Okay. So let's give it a shot. So that's the old Sigmoid, the handcrafted one, and this is the one that we want to fix or change. I will just wait for 1 minute for this to be done, and really I should be able to just run this bench and only this one. Yes, please. It will be long enough running one. Pum 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 pum. I will try to find a better setup than this. I mean, I have essentially dozens of Raspberry Pis all over the place, and I don't think I have a single one which is in close proximity to the PC I'm using right now. So that's, and when I say in close proximity, it means below hundreds of kilometers. And okay, so it's working. That's good news. And I'm only interested in Sigmoid for now. So yeah, I'm next time I'm in the other place in Paris. You can see I'm not in Paris right now. I'm going to try to fix this because it's been a pain for these sessions. Okay, so that's the reference implementation. That's the generic implementation, and this is the ARM implementation. We are looking at the number of elements per second. So here we are running 82. I mean, the reference implementation. What was it actually? Is it the Rust one, the Scala one, the one? Yeah, it's the one with let p equals alpha something, etc., etc. Not even sure about this actually. Yeah, it has to be. Yeah, but that's the generic implementation of the virtual machine. This is in handcrafted assembly. And this is the assembly that, the interpreting assembly that we are working on. And it's really only interesting starting with 500 or 1,000, sorry. So let's have a look at 1,000. So the reference implementation is actually pretty fast, if I remember correctly, at 200 million of elements per second. The Rust interpreting is 10 times slower. The interpreting in assembly is 5 times slower. And the handcrafted is not better, which is super weird. I think we might have a problem because yeah, this one should not be faster than the handcrafted one. Okay, let's not focus too much on this for now. Let's try to make it work. So what I wanted to do was this. So essentially, this means that instead of doing FMLAs, I will be doing fmul, then fadd. The reason why FMLA, well, I can't use. I mean, ideally, it would be nice to be able to do it with just one run at FMLA. So problem is FMLA in ARM does this, and you cannot pick which register does what. You can on Intel, but that you cannot on AVX2, for instance. but you cannot choose on ARM. It's always an accumulation, and the two registers are multiplied and added to the accumulator. You cannot change it. And so as the value on which we accumulate is a constant, we have to prepare ground with copying it all over the place like this. So this is a dup here, plus what? Come on, where are my fingers? So this is the duplication of the constant, and then this is the FMLA. Plus, and this is related to the way our interpreter is baked, we cannot do the same trick that we found in the handcrafted one, where we use one register, then the other, and back and forth. We have to, we can always, we have, I mean, it has to be A all the time, or else we will need to extend our operator set even more. So I think that this could give us good results. So let's say, first I'm going to do, and we already have this instruction actually. So it's a mul, so that's this one. And this guy is add const, which I also have. And that's it. So I'm going to comment out all of this block. And I think we should be done. And so the fun thing is, we could actually write these replace the FMA in the macro language by the mul and the add to get the same result. One more thing I want to do is, here I have a dependency chain. These instructions have to wait for v24 to be set to execute. And v24 is just set here, and it's actually set there. No, it doesn't matter actually. I thought that we had a load, but the load has been done way before, so that code should be reasonably fast. If, for instance, here, if I were loading, so it would be what, LD1. Yeah, if I were loading. Hello TPX. If I were loading v24 from memory, then I would have a long dependency chain here, and it would make sense to move this there. But actually, the value has been loaded already, and this stuff is just working with registers. So nothing there takes more than a cycle, so we can leave it there. It means it doesn't make any difference, and it's easier to read. Okay, trying again, and we are looking at, we will pick this one, I guess, and we will stop looking at the others for now because it's too depressing. Up. So the bench will run faster, but unfortunately it will take the same time to compile and also to copy over half of France before we can see the measure. So that's a promise. Next time I'm in Paris, and that's going to happen this week. I'm leaving a device, a Raspberry Pi over there, for this installation step to be faster than it is today for the next sessions. Here we go. Five seconds. Okay, it's a bit faster. It's not super faster. It's a bit faster. It's just a bit faster. So why is it so? Well, if you look at what we've done, the sigmoid is essentially made of these long polynomial computation, two of them. And so if we only have, and really, I mean, the impact that it should have should be massive, because unless, and I don't think so on the Raspberry Pi 3, we have anything smart, because CPU is a Cortex A53, and these chips are pretty dumb. I mean, they just execute instruction in order. They don't do anything magic. So I'm pretty sure, and maybe we will try to measure it later, that what we observe is really what we asked, in terms that it didn't rewrite the sequence of instructions. So if we only have a 6% improvement by essentially discarding one instruction out of 3, this means that we probably spend a lot of time in the interpreter. And that's interesting. This is interesting. Why? Because first, I mean, because that's something that we can test, and I guess we will do that pretty soon. And also it's something that we can solve, because what we are doing today, it actually doesn't have to be an interpreter. We can essentially compile this by, I mean, we can compile the function, sigmoid function, instead of interpreting it and having to go through the loop. We can just do it by hand or doing it later by script, but basically we can get these chunks of code that actually implement the micro operation, and we can just concatenate this sequence of instruction, and we should not have, I mean, we should solve a big part of this overhead. I'm doing fine, thank you. I don't know who you are, because unless you're called unresolved error, my screen shows you as unresolved error. So maybe I should reload Twitch. Let's see. Oops, reload is the wrong screen. Come on. It's your name, okay. And my Firefox is stuck, which doesn't matter. Okay, let's leave it alone. So hello, unresolved error. No, it's not horrible. It's fine. Okay, are we back? Yes, I think we're back. All right, so what should we do next? Because this is, I mean, if we spend so much time, rest and assembly, yes. If we spend so much time in the interpreting part of things, then we should just probably ditch the interpreter. So I think our next steps is to try to put some numbers on this and decide if this is what, I mean, if what we think is what is happening, or try to get some hard data on that. Learning C++. Well, consider Rust. C++ is super hard. Oh, for the 5th time. Yeah, so you know about it. Yeah, it's I really hate it. I mean, I stopped. I won't tell you my life story, but I stopped doing native development like 15 years ago. Even 15. Let's say 15. Because it was all C++, and I was so bored with the stuff that I had to change. No, Rust is much easier. I mean, it's a bit harder to learn. Some people would say, but I disagree with them. It used to be. It's no longer true because documentation has improved. Compiling messages are good, and it completely prevents you. Yeah, and it completely prevents you to shoot yourself in the foot. I mean, it would be the same if I were doing C++. I mean, other frameworks are doing the same in C++. I mean, what I'm doing in Rust, I'm doing it in C++, and they have the same kind of assembly all over the place. So that was a low blow, typics. Okay, so how could we try to measure the performance of the jump table and interpreting stuff? So, what we could do, before we do that, because I'm not 100% sure it's this, because there is something else that happens in the computation of a sigmoid, and it's the division at the end, and division is super expensive. So, it could also be a problem, I mean, the problem could also be with the division. So, what we could do first is time each of these simple function operation and see which one take time, which one are fast, and which one are, I mean, try to see if it makes sense. And what we are going to do is we are going to add, right away, we are going to add an op one. My screen is all messed up. Okay. Come on, Tmux. Okay, back. Why am I writing assembly? Because I'm doing essentially high power computation on low power devices. So typically phones or smart objects. And in this situation, and computing neural networks. And in this situation, there are quite a couple of cases where you can really beat the compiler. And I mean, even C, you can beat C easily. C, C++, and Rust will be in the same ballpark. And by doing stuff in assembly, you can really squeeze more performance. Not necessarily on the activation function problem that I am playing around with, let's be honest. I mean, it's probably not super efficient to do that. But on the matrix multiplication problem, you can really, I mean, you will not get a factor of 10, but well, maybe you will. So, yeah. No plan to switch to RISC-V. It already works. I mean, Rust natively supports RISC-V, and I've tested Tract. I actually have, it's not over there, it's in the other room. I actually have a device, a board with a RISC-V computer, but it's not super fun to code because I mean, at least this board doesn't have vector instruction, so essentially you just let the compiler do its stuff, and that's about it. Okay, back to this. What did we do? We did this, and that didn't bring much. We will still do something. We'll test it, just to make sure that it's good. Yeah, no, that's a bit true. But I mean, it's kind of hype. So being able to say, hey, my engine runs over RISC-V boards. But really, I wished. I mean, I bought the board, and it was super hard to buy because it was in the middle of COVID, so all the supply chain were broken, and so I managed to get a board, and I thought it would be a board with a SIMD, I mean with a vector unit, and it was not. So I mean it was I was super sad because yeah, no fun to get. Just plugged it, compiled it, and hey, it works. That's it. I'm done. So yeah, yeah, if some way I can find a board, a RISC-V board, when I'm done with activation functions, maybe we can have a look at SIMD over RISC. But I mean, maybe now there are more choice, more options. I don't know. Do you know TPX? Yeah, I've seen specs for them. So, but it's also, I mean, RISC-V is pretty complicated in that it's spec that aggregating specs, and it's not super easy to figure out what you will get. I think. I mean, ARM is a mess too. ARM8 is okay, but ARM7 was really messy. Because sometimes you have VFP, sometimes you get Neon 3, Neon 3 with only 16 registers, Neon 4. I mean, it was a bit of a mess. ARM8 is simpler. Yeah, I'm not sure that there is one working implementation of it. I see lots of green, so I guess what I did is correct, and it seems to bring a 6% performance boost. Woohoo, 6%. So I think we'll keep it. Okay. No, wrong file. Activations. So we said that we're keeping the new implementation. Where are you, activation? FMA. Okey-doke. So what I'm going to do is committing this first. Replace FMLA by. So this is actually not completely neutral in terms of the results. Because when you do FMLA, there is no rounding between the product and I don't remember. I mean, I remember that there is a rounding that goes away. Whereas when you do mul and add, both rounding happen. So the result is not strictly the same. But for neural networks, I mean, the precision of F32 is too much. I mean, everybody wants to work with F16, and bless ARM64 for ARM64 v8.2, where we finally have half precision instruction. So this same except with 8H instead of 4S. So we can do twice as much in the same time. And as in neural networks, the information is really not in the last decimals of your values. It's just spread over a huge number of value. Being able to use half precision is a nice performance boost, and it virtually comes for free. Anyway, so what I want to do is I want to add, I don't know what ARM-sum is, to be honest. But what I want to do is I will add an op instruction, because I want to measure the interpreter override. Yes, okay. So this happened in frame. So frame contains the Rust code that drives these assembly routines. And in frame activations, we have, so this is our high-level instruction. So these two ones are not implemented yet, because even swap BC, because these are the ones that we need for exponentiation, but we are not there yet. For for now we will add nope. And so in this big table translates the high level instruction to the lower level instruction, the one that we actually push to the kernels, to the assembly routines. So in the case of an op, I will just do a simple thing. So it will be a op const, and the op will be a kernel op nope. And so here I have the table for the kernel ops, and so I will, so these comments are used to generate the jump table that we use in the interpreter. And so nope, here we go. So I'm going to check, and it will not compile. Why? Because I also need to implement it in the generic Rust fallback implementation of the activation. So here we go. So this is essentially, I mean, there are some differences, but it's pretty close to being equivalent to what the assembly code does. And here I'm adding char op nope, which does nothing. So if I'm doing nothing, I'm doing this. Yep, because I was looking that some instructions have to push lower in the instruction flow because the instruction flow contains both instruction and the constants for the constant operators. So the operation that takes a constant have to do this to skip the constant before moving on to the next loop. Okay. Is it worth adding a test for this? Testing nope. Does it make sense? Let's leave it alone. I mean, it probably won't stay, so we just, here we are just testing on Intel that we haven't break anything with these. Yeah. Well, I mean, you can see the number of tests that I just ran. So maybe I'm doubting a lot, but when I'm doing assembly, I'm actually writing more Rust than assembly because for, I mean, like each line of assembly, there is an entire framework of test and bench in Rust that keeps me safe. So the Rust code is essentially safe. Not all of it is safe in Tract. The assembly code is very unsafe, so I'm testing it a lot with many tools. Anyway, so if I'm doing this, it should not even compile because it will generate a jump to no-op, which might not be a great choice of instruction name in the ARM64 assembly. And so as long as I haven't, yep, here we go. So in function jump table, undefined reference to nope, bingo. So this was anticipated at least at F32. So I'm going to add one here. And so no-op will just go back to the next instruction in the inner loop. And so the test should work. It compiles and it will work. Not too worried about this one. Okay, so now what we want to do is yes, so what was the reference Sigmoid implementation? It doesn't matter. Later. So now what we want to do is we want to bench. So what we are looking at here is the benches that we tried before. And what I want to do now is I want to bench simple instructions from so it will be a different bench because this one takes a reference implementation, so a function of floats to floats, and the program, which is the decomposition of the computation in our macro language. And it will compute, it will bench the reference implementation by just doing a for over the reference implementation. And this for VM in VMs. Why do I have several VMs? Where are they coming from? VMs. Okay, so I just have one of them. Okay, yeah. So I'm starting with the generic VM. So that's the run in Rust that we saw. If I am on the ARC64 target, I add to the list of VMs the one in assembly. And then I loop over all of these and essentially run the program. If by chance we are working on Sigmoid, I also, and it's a bit of a blister, I also add the handcrafted Sigmoid implementation that comes from here. Okay, this will be inconvenient for us because we don't want to bench against a reference implementation. We just want to bench single op or maybe 2 ops or 3 ops in sequence and see how our interpreter behaves. There's a bit of a formatting mishap here. That one can probably go away. Okay. So we'll call this end-to-end benchmark. Okay, and we're calling this one end-to-end. Putting an S there. And so I'm going to add single op, or let's call them unit benchmarks. So same, I'm going to use Criterion. Criterion is a pretty good tool to write benches. And so I'm going to create a group. For now we call it units. And should I pick several size or will one size be enough? Let's do this. I want the throughput. And so I will also pick this bit of code. Maybe I should make it a function. Oops. Yep. So these is a vector I mean, I have the type over there, box of din activation, vector of box of din activation. This has to be this one, yes. 1, 2, yeah. What's wrong now? Missing generic, yeah. And I just need to return VMs. The annotation should have come there. Whoa, TPX wrote me a novel. An efficient way to gain cycle assembly is to not respect the ARM GNU EIBI. Yes. Yes. Yeah. I am painfully aware of this. I thought about it because there are many ways that this can play, and the problem is I don't know how to control what Rust will do. For instance, I could write the assembly in Rust. I mean, it's a bit extreme and it wouldn't work. Yes. Well, I mean, the point is, I mean, being crazy is fun, so maybe one day. But there are a few things that I would like to do, but I don't understand, and I don't think that the compiler gives me the right constraint. But when you write some inline assembly in a C or in a Rust file, there is no way to say to the compiler, okay, between this block and that block, do not mess with the vector register, or do not mess with this and that registers. Yeah, I mean, between my code and my code, I can do whatever I want, for sure. If I want to break the convention, that's fine. It's just, yeah. I'm not sure how much I would gain with this, but at some point I was thinking I would like to write the interpreter in Rust and just have chunks of inline assembly, but I don't think there is a way to say to the compiler you do not touch a couple of generic registers, or you do not touch the vector unit at all between this block and that block. So I guess it would not do it by default, but as there is no warranty, I just don't want to risk it. Okay, so now we can iterate on the VMs for VM in VMs, and we will reuse that bit. So size comes from here. Benchmark ID is made with the name of the VM and yes. So here I just have units. So probably what I should do is I should take the name instead here, and I should take the program I want to test here. Program. And this would be a unit one, not unit benchmark, because it turned into something that just does one. And so I'm getting a vector ready with this, a vector of ones and of size, and I'm running prog over, okay. And so I will need something like this to define a series of bench. So unit benchmarks. Unit benchmarks. Marks. Let group. Let group equals, so I still want here, so here I'm going to set name, so here I will keeping unit, that's good, except now I'm not giving git criterion, I'm going to give it a group. Let's see how it works. And so first I want to do is I want to do unit of the group. Okay, let's do this for now. C. So we'll say no op, and the program will be just care. So yeah, it's program, and ops is, I need to simplify this type now, because at some point if you follow other sessions, there was, operations and constant was separated, so but now they're just operations in the program. So anyway, op is vec, and it will just contain an op. So it's care, it's op. I need to include, yep, and nop. Here we go. So I'm also going to do empty. Sorry, like this. And I'm going to do nop2. Probably I should try and fix whatever is wrong before copy and calling it again and again. Program blah blah. Yes. So now what? Invalid. Yes, now it's a bench. Cargo dinghy, -d, bench, -, minus bench, activations. And it should not compile. I'm just running it like this because I can see the full error message in VI. Okay, I'm not using the name because I don't need a name. I don't need a program here. And I'm just going to call unit benchmarks. Here we go. And I'm going to limit it to activations, units. I need dash dash to split arguments. Pum, 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 pum. Great, didn't do anything. Yes, because, yeah, I wanted to do that. I wanted to prefix all of them by unit. And then he said that no, it was useless. But actually it is useful. But now the problem is, it will be a, wow, super difficult problem. I need to change the type of the other guy. And I didn't use the type. This is why I didn't do it. So, found benchmark group. Oof, it has a lot of stuff. Benchmark group. and I don't know what to put after that, so it wants a lifetime, which I can probably do without, and M, which is what? Measurement. Okay, what about if I'm doing it like this? Is it happy? No method. Oh, I cannot have a group in a group. Okay, so let's cancel all of these. And instead, I'm going to here, I'm going to do something like that, format units. Yeah, this is ugly. This is ugly. And so if we discover that the interpreter override is big, then we have to refactor a lot of things, because I mean, we have to copy, to move a lot of stuff around to be able to concatenate the chunk of assembly in the right order, in the right place. But it's not super hard. Just I really thought, I mean, it's not empty slash unit. I wanted unit slash. Why did it do? Ah, yes. I put it in the wrong place. But it's okay. We'll let it run. So what we are going to do is we are going to look at yes, and I could have skipped generic. I think what we want to look at this number, which gives us the time that the program needs to run. So it's about, if I'm looking at this number, I'm going to fix that because it's hard to exploit like this. So I want unit slash name. Here I can use VM name directly. And I'm going to require so yeah, okay. Problem with this is I mean, that's a limitation of the filtering. I would like to do empty, I mean, so it's unit empty blah blah 8000. So I would love to be able to put a star in the middle, but I can't. It's not supported by the bench selector. So we will do it like that, and we will tolerate seeing again at the other ones, or if it comes to that, I'm going to comment the code so they're not I don't know if they will come in first or in second. I guess they will come first, the end-to-end ones. So let's try to save a bit of time. Installing. Nearly there. Okay. So 2 microseconds, that's consistent with the one before. And the knob, it looks like, I mean, there is not a huge difference. There is a 0.2 microsecond or so. Yeah, so we are not great here because we are in, I mean, there is some variability, so it's going to be a bit hard to exploit. 2.4, 2.4, 2.2. This one, I mean, on this one there is a huge variability, which is a bit of an issue. Okay, so what we are going to do is we are going to do this. So we have some kind of fixed cost at around 2 micro. I mean, for this size of vector, which contains a lot of things because we still have to move the memory around the 1000 values. And on top of this, it looks like we have a 0.2 micros for each no-op instruction. That's what this suggests, more or less. I mean, the weird thing is that there is not, I mean, here we have, and it's pretty consistent, so we have 2.2 and 2.4, but here the problem is we only have 2.17 to 2.22, so that doesn't make a lot of sense. Okay, so yes, we have variability on the first one. 2.4, that's no up to 2.2, 2.25, 2. Okay, so it grows. Okay, and then we have 34 micros. Okay, so 34 micros minus 2. 32 micros for 100 instructions, no-op instructions. So each instruction seems to cost us 0.3 micros. If I mean, yeah, it's a ballpark. Now let's try more fun ones. So let's try, for instance, at const. Let's try mul. I will also do sub. For fun, we will do div. And of course, we are going to do FMA. I don't have div const. Yeah, I don't have this one, so let's just skip it. Maybe FMA should be called FMA const. And so there is, I can do this. So nope was empty was clocked at around 2 microseconds. Micro, know where you are, so that's Raspberry. Easiest way is to copy the command line. So empty clocked at yeah, that was the one before. So now we are clocking nope 100, nope 100, 33 micro, add 100 is 53 micro, sub 100 should be the same, 54, mul 100, 77 US, and FMA, so no, mul is also okay, and FMA is 77. So it's relatively consistent, I think, because so one of the good thing is add and mul takes the same time, and that's because it's pipelined. So when even if the multiplication takes, like on this chip, I don't know, it's probably 5 cycles. It's a very dumb chip, Cortex A53, but it's still pipeline. So so the multiplier starts and the result is not available for like 5 cycles, 4 or 5s. But it doesn't matter because we are not needing them right away. We're not using them right away. And that way, even if the multiplication is significantly more expensive than the addition, they roughly take the same time. So that was expected. Now, if we look at FMA, in our case, we do first the multiplication, then the addition, and we do them by hand if you went there at the beginning of the session. And we have an overhead of like 20 something microseconds, and that's roughly in the ballpark of the nope. Yeah, that's not true. Yeah, okay. So this means that doing the add is actually like 20 microseconds, because that's this is a payload. As in, I'm discarding this the 33 microseconds which comes from the interpreter to this to this 53, and so actually when we do that, we see that the interpreter is taking half of the time. More than that, because the interpreter is costing this, and actually doing the work is just that. So it means that we will have to, I guess we will have to get rid of the interpreter and actually compile our stuff, which means a big refactoring of everything we've done so far. So we won't do it tonight. Because basically this means that in the current situation with an interpreter, I'm compiling tract once, and then I can, as it's an interpreter, I can provide it with a program. So when I have, Sigmoid or Relu or Artwish are just sequence of operations that are, not code, it's just data in the program. But if I'm moving to compiling them, I need to generate function for them. And so Sigmoid and R-switch and ReLU, for instance, become actual functions of the system, specific ones. Which doesn't mean I cannot keep the assembly for new ones. I mean the interpreting code for new operations that would come later. But if I want to be fast in this, it looks like I cannot do it like that. I mean, it looks like the interpreter is costing me too much. And that's not great news. To be honest, I had foreseen that a bit. I'm not super surprised. If we look at the issue, yeah, it was there. But I thought that it would be less. It would be less bad. Does it make sense? Does it make sense that it takes so long to switch, to jump around and to decode stuff? I'm not too sure. Yeah, also, I mean, this is for 100 instructions, so actually, if we want it, yeah. If we want it in so for instance, if I'm looking at the add 100 case, I have 1000 value to process, and I'm doing 100 addition. I'm trying to figure out how fast it could go if I was just sequencing the instruction, and see if it makes sense, if it's in the right ballpark. So 1000 addition, 1000 number, sorry, on which I'm doing 100 additions. So that's 100k ops, and I'm doing them in vector fashion. That's 25k vops. Now this sheet can take one vector instruction per cycle. Vector op per cycle. So here I'm talking about SIMD instruction, not the big instruction that we are designing. Let's say one neon vector per cycle. And so that's Intel machine. It's a Raspberry 3, so Raspberry 3 is 1.2 gigahertz, I think. One dot 1.5, 1 dot Raspberry Pi. So there is a big table. There is a big table here, and Raspberry 3 1.4. Okay. So 1.4 neon vector op per second. So 1.4 billion of instruction. So now, if I'm doing the right division, will I find my fits? I'm not sure. So if I'm doing it the other way, so 1.4 giga ops times 4, so that's 7, it's 6.4, no, 5.6, yes. So this is the number of ads per second, for scalar ads per second. Okay, I'm just, I mean, as this ship can do this ship can do 1 vector ad per cycle, okay? And each vector is 4 scalar long. So this is a 5.6 billion of addition per second. And we are doing 25k ones in 0.53. So 25 divided by 0.53, and so these are micros, so I still need to multiply by is it right? No, I already did I already divided by 100 here. So that's not 25, it's 0.25k, so it's, sorry, it's very confusing, but it's always like that when you count instructions. So let's try again. We are doing, okay, let's put it back as it was. So here we are doing 100 instructions. So that's this instruction in 0.53 micro. And I'm lost again. Yes, here we go. So these are millis and these ones are micro. Oof. And that's a big number. And it's way too high, so something is wrong. Something is wrong. It should be in the range, I mean, it should be, oh, no, actually it's fine. No, it's wrong. No, it's fine. It's 471 millions. Okay. Yes, it's actually quite good. I mean, it validates a lot of things. It's consistent. So I'm just checking that I wasn't confused. So 471, yeah, million of operation per second. So that's actually megaflops. And we have a capacity theoretical of 5.6 gigaflops. So this number is 10 times this one. So yeah, so what does this mean? It means that we are not using we are not going as fast as we could. We should be, I mean, we should aim at being higher than that. And there is the overhead of memory. So if we want to try to cancel or to erase the overhead of memory, we could try to do, instead of doing 100, we could try to do 1000. There is still a bit of memory access because each instruction has to be fetched from memory. Also the constant Raspberry 3 are ARM64, yes. They are Cortex F53. They were crippled for like 10 years because Raspbian was only shipping, Raspberry Foundation was only shipping Raspbian, which was a 32-bit operating system. And because that's the one they designed for Raspberry Pi 1. But you could use Ubuntu 64, and now I think Raspbian is a 64-bit operating system too. So yeah, Raspberry 3 is a Cortex A53. Okay, so this means that there is some margin for improvement, and I guess I'm not going to jump into this tonight. I'm going to think about it before, because I need to find a way. I need to figure out a way to not make it ugly. It was kind of okay, but I will basically need to split all of these blocks. Where am I? Yeah, I'm in the right place. It's fine. I will need to basically make all of these blocks chunks of code, and then assemble them in the right order. In the sequence order, and put them in a file and compile them with Tract, and give them the name of the operation they are doing. And we'll see. We will do it. Or we could do that actually. We could generate. Yeah, let's do this. Let's do this. I'm going to put a lot of these ads, like 100. Writing the assembly is the easy part. The more complicated part is to get it to run. No, I won't do it tonight. I need to think about it, about the right way to do this. I need to sleep over this. Because yeah, I'm thinking about this. I do not come completely unprepared. Yeah, so this will have to. This will be for next week, I think. So I'm going to stop right there. It was a short one, but interesting one, I hope. So, well, 4 viewers. I guess that's nearly my record. Congratulations, people. Thanks a lot. And see you soon.